should record because Sydney's not here actually. All right. So let's start first with this first one. So tinkering. So the whole premise of the concept of engineering is thinking about devising things, contriving different things. And that's what we're talking about here, the etymology of it. So when you're a little kid and you like building stuff, usually that's like a sign that somebody who maybe later in life would want to be someone that works in a mechanical engineering field, or maybe a civil engineering field. Or maybe you're a kid who really loves computers, or computer science, computer coding. Or you love understanding like performing science experiments when you're a kid, maybe you're a chemical engineer. So this is just a progression of where like engineering, you see it in younger children and then like later in life. So let's get to the next slide to see these three modes. So first, as a kid, we're talking about somebody who's like a tinkerer or a problem solver. And then as a student, usually with engineering, most students that want to study engineering in college have a tendency to enjoy science and enjoy applications of math, really physics and science. And then as a professional, obviously, as an engineer, you're going to be doing anything, really. And that's the biggest thing about engineering. Like, for example, I'm a teacher today, clearly not working in engineering. Both my degrees, under and grad, are both in engineering. That opened up a world of opportunities for me as far as jobs are concerned. You could have you could have a degree in engineering undergrad, not even go to grad school, and easily get jobs in the business field with an engineering degree. Easily get jobs in medical fields if you have some training in those areas. So it's a very good, I don't want to say degree to have, but it really is. It's very useful in any form of your job later in life. So as a professional, I don't want to specifically say, oh, you're going to be working in engineering. But if you do study an engineering field in college, it's a very useful degree to have. If you do go on to study engineering and not only study but work in engineering, you then also become what's called a professional engineer. And in your college time, you take what's called the fundamental engineering exam. And then later on, after you have like 5 or 6 years of experience working, you take what's called the PE exam, the professional engineering exam. And these are exams that you have to study for, like GMATs or like your LSATs, the law school. They're not exams that are going to be like an easy exam. The fundamental engineering exam in college is very difficult. You can take a broad one, which covers a little bit of every type of engineering. And that's tough if you don't like know a lot about chemical engineering because you're mechanical. You could also take a specific fundamental exam that is in your content area, all in mechanical, all in civil. That is much tougher in that area, but it doesn't cover all the other areas. So it depends on what you really like in college. If you're into all the different fields, you might take the one that's more breadth. If you're into really mechanical or civil or chemical or computer, you'll take the exam in that area. So fundamentals in college, and then with experience, it's called the professional engineering exam.
What's like the format of the test, like the type of questions that are asked?
It'll be problem-solving types. So I did not take this exam, so you know. I did study for it. Could have taken the exam, but I didn't think I was going to be an engineer after college. I continued enjoying studying. I didn't take it. But studying for it was, I think if I recall at the time, multiple choice and then free response. Similar to like an AP style exam. Heavy math, heavy math. Heavy reference table. So for example, like if you're civil engineering, a lot of the civil engineering work that you will use later in life comes off of certain reference tables. You'll hear that from like mechanical engineers, not if your parents are civil engineers, are not taking a stab at that. When you hear from mechanical engineers, and mechanical engineers do the heavy math to understand it, and civil engineers just use reference tables. Meaning, like a lot of what you do is already been discovered. Is that the right word? Yeah, not invented, discovered would be the right word. And then you apply it on the exam. So let's say there's a structure, there's a certain cross-sectional shape, and has a load applied at the end of it. You can use a table to look up the table and say, okay, is that a box beam? Is it an I-beam? Is it a W-beam? Well, the different shapes of beams for this example for structural, and then you apply that force at a different location and determine how much torque is actually there. What is the support that we need at the end so that it doesn't snap or break out of the wall? So on the exam, you'll be using reference tables and data tables also to come up with your conclusion, but it depends on the exam. So if you're a chemical engineer, a lot of the data you're going to probably be given would be like stuff that's on a subatomic level. Knowing certain properties of different atoms would be given to you and you have to apply them. So maybe you have a periodic table on that exam, whereas the civil exam has a table of all different values of structural analysis. So the exam is going to be a very broad exam if you take it in all the areas, but very in depth if you take it in the one area that you're studying. I like to say that an engineer also later in life, not just as a professional, is somebody who wants to always learn. And learn really just how stuff works. So, you know, the show, how stuff works, or how it's made is the show, and then there's the website, how stuff works. That is the kind of, if you're into that kind of stuff, engineering is probably a good field for you to be in. Now, it doesn't mean that if you study engineering that you have to also be into exactly that. Maybe you study engineering, but then you go into architecture. Still, the concept of learning how things work and designing playing a role in architecture. Okay. The next slide is simply a couple different definitions of engineering. I'm not going to sit here and read through everything. But the common thread amongst them all is italicized. So what's the common thread amongst all these definitions of engineering? It's an application. It's an application. Engineering is about taking math and saying, where can we use it? And that's an ongoing question, right? Because when you're a kid, you learn math, you learn the basics, and your first question as a kid, and as a child in general, is why? Why? Why is a question that's asked by a child, like, I think, until you're like 5 years old, like, a child on average asks the question why like 50 times a day. Because you just want to learn why things work and how they work or why they happen. Well, in this case, this is the idea about applications. Why do we learn math? We learn it to apply it to other things. Learning math does us no good if we're not going to use it. Right? Think about it logically. If I want to invest money and become an investment banker, I need to understand the concept of compounding interest. I need to understand the concept of long-term investment versus short-term. It's all math that teaches you that. So the concept of an application is why it's the key to the type of, or the design or the structure around engineering itself. Okay, a lot of definitions you can read through those. I'm not going to sit here and just read them off. All right. So some characteristics of engineering. First, the first one is one that I've talked about even in physics: optimization. Optimization. What do I mean by optimization?
It's like kind of making things the easiest that it can be. Like
Okay.
by using just using things from all different areas of something like that, especially.
I like it, making things as easy as possible. Maybe something else. There's a lot of ways to describe it.
More efficient, something.
More efficient, good. Easy to work with, more efficient. You could be talking about the manufacturing process. You could be talking about the sales process. What else? What other things you would traditionally want to optimize? In any field, really. What would you want to optimize? Profits, so maximization sometimes of profits. Efficiency in general. Sorry. Excess cost, minimization of cost. Good. So the concept of optimization is this. Either you are maximizing or minimizing. Now, there are times that you want to take a route that gets you to an exact value, and that's a different optimization technique. That's using constraints to see what your limits are to obtain a specific result. So for example, if I wanted to make the most out of something, if I wanted to make something as strong as possible, right, as strong as possible, I could put a ton of money and research into it and have a structure that will never fail. But that's not reasonable sometimes because of the fact that you probably can't sell that structure, or that item, or that product, whatever it may be. So it's not always the case that you can minimize your costs completely, or you can maximize your strength or your robustness of the product. So sometimes you find a compromise in between. So the idea of maximization and minimization is what you're really basing it off of, but you're not always going to get the best result for one area because there are other things to consider when developing that product or service. Okay? Like for example, if I tomorrow were designing a new car share service, right? There's Uber, there's Lyft, there's Via. There used to be one called Juno. There was one called Get for a while, GETT. There were like 7. Now it's really Uber and Lyft that control most of the market. If I want to design a new one tomorrow, optimally, I would say I would make the cost $1 for everybody, and everybody would take my ride, right? Because it's the cheapest cost, and every user would want to take that. But that's not reasonable, because within 2 months you're gonna fall through it. You're gonna go under. You know what I mean? It doesn't make sense logically. So you have to find a compromise at different times. Okay, constraints are very similar to what I gave you on your physics projects. Limitations. So for example, you probably cannot build something out of carbon nanotubes, even though they're the strongest material that we really know to man right now, because it's so expensive. So your constraint might be a budget. So you've got to have a cost constraint. What other constraints might you have?
Size.
I can hear you.
Size.
So, geometric, good. Geometric constraints in general. Location, geographic constraints. Materialistic. So you mean materialistic? Oh, okay. Materials for sure. Like, there are only certain resources that you can use, that you can actually utilize. Okay? Time. The most important constraint there is, by far. I diverge sometimes in what I do. So when I was younger, my dad knew that I was really into science, and he was not. So anytime he could find something that we like shared an idea of, he would try to make a point to do it. Because I would love to talk about science and didn't really understand it, or like just didn't have a knack for it. So when I was like 10th grade, so I was like 16, yeah. So I was like 16. My dad, I was in like kind of physics course at that point, yeah. And he knew that I was really into it and said like, I have this. There's an opportunity we can go to this lecture. And at this point I was like, oh, I'm going to a lecture or some sort of a presentation with my dad. But then he started telling me about it. He said, and to keep me engaged, he said, the lecture is titled "The Most Important Resource That Exists." Now, based on my conversation or our conversation, you probably know what I'm going to get at already because I said it. But when I was in 10th grade, all I was thinking was this: oh, it's money. The answer is money. That's the most important resource. Or air, or water. Water is the most important resource. You can't live without water, right? So the whole ride over, he and I were talking. I never thought of time as the answer. And the whole presentation this guy gave was about the cost to benefit ratio of your time. And it really helped me a lot to recognize how important time is in your life. It's something you'll never get back. There's a ridiculous movie with Justin Timberlake that was out like 10 years ago. And the movie the premise was this: when you're born, everybody has only a certain amount of time. And when you were born in this world, it was a sci-fi future, you had a number on your wrist. And that number was constantly counting down. And it was literally the amount of time you had left in your life before you would expire. I don't know how the world worked. I never watched the movie, I just saw the premise. But the idea, it sounded terrible news. But the idea was that there were people that over time, realized that the most important resource was time, and because they had money, and other people maybe didn't have money, they would buy time from others. And they developed a machine that pulled like the life source out of your body into the other person as a result of a transaction. So let's say, Alex, you were homeless, and you have and you have 20 years left on your life, and you really wanted to get food tonight for dinner. You could sell me some of your time on your life, and I could pay you for it, and you could get dinner. So the premise of the movie was that, like Jeff Bezos, Jeff Bezos, right? I like Amazon. Anyway, so people like Bezos or like people that were like ultra rich were pretty much buying up everyone's time in the world and living forever. And the whole idea was, to be immortal. Anyway, the point being, time is by far the most important resource. It doesn't matter what job you're on. It doesn't matter what career you're working. Time is the number one resource because without appropriating your time properly, you can never accomplish the goal you aim to. It doesn't matter how much money you have. If you don't use your time wisely, the money isn't going to be the answer to what you need. So time being the most important resource. Anyway, it's one of our constraints.
It's called In Time.
Is that what it's called? In Time? What are the reviews? I'm curious.
Yeah, let me see.
Rotten Tomato and IMDb is probably going to get 2 stars.
37%.
What is it?
37% Rotten Tomatoes.
And that's probably the fan rating too. The critic rating is even less. Yeah.
So, you mentioned carbon nanotubes. Why are they so expensive?
Why are they what?
So expensive?
Because they're grown in labs.
They're grown.
Carbon nanotubes are grown physically in labs.
Something with like.
So it's like a graphite structure that's really strong, but it's really expensive to make. So I'm not a chemistry person, so if you want to look it up, you can maybe tell us more. But carbon nanotubes are not something that like just exist. They're grown on an atomic scale, and then they're tested and they're used in different applications. Nowadays, it's more, I think, electronics that they'd be useful for because of the scale and the size that they'd be used on, not macro scale. Third characteristic of engineering is modeling. And by modeling, I don't mean modeling like modeling clothes. I mean modeling is in making models for items or products or services. So 30 years ago, when I wanted to invent something, what did I have to do? What did I have to physically do? Patent it, good, I like that. What else do I have to do if I wanted to invent it? If I wanted to invent something, what do I have to do? Make a prototype. Very good. Make a prototype. Modeling is about prototypes. Am I going to make a prototype for everything nowadays? Probably not. Why not? What can I do instead? Exactly. You run computer simulations and models that give you results before you actually pay for the testing. Now, if the computer model works out well, you might then put forth money in a research and design company so that they can actually build and utilize or test it in the real world. Because again, computer models give you the ideal solution. Now, computer models do take into account certain things. Like, for example, when we were in physics, I would always say, more error resistance, right? It's negligible kind of thing. For computer models and certain things, they're going to take into account that kind of stuff. So, if it has to do with the air resistance on a new car that they're designing, and they're having a computer, what's called computational fluid dynamic model, CFD, they'll run these CFD models over the car to see how streamlined the air is, to see how little or much resistance, friction there is due to air resistance. So modeling is a very useful thing to do, especially nowadays, because we use a lot of computer models that save us money. We don't have to build it and test it right away. We can think about it first, design it, and then start building prototypes for it. Okay? So modeling is number 3 thing. Responsibility. Oh, so responsibility is taking on responsibility to have a product or service that is A, safe for human consumption, use, whatever, B, moral and ethical. So by responsibility for engineers, sure, I could cut costs on my product, but it might have a cost of human life. So if I'm building a bridge, would it make sense to cut costs on a part that is needed to hold the bridge together? Of course not, right? It would make sense. But you know what? If I'm building like a really cheap, crappy toy that I don't care about it being reused over time and I'm okay with it breaking, and it's like a fad maybe, like remember the fidget spinners?
Yeah.
Remember fidget spinners? They were popular for like a year. Did it matter if the fidget spinner was like perfectly made? Not really. Didn't make a difference if like one of the edges was a little bit different than the other. You didn't have to worry about safety. So different items have different implications, different services. Go back to the rideshare services. I took an Uber last night, and you know when they drop you off left or right side of the road, it makes sense if you're on the right side of the car and on the right side of the road. Uber has not figured that out yet. And they're really going to get sued one day when somebody opens the door and gets smashed by a car coming by. Because to this day, they should have some sort of application in there where the driver, him or herself, should recognize if you're in the back right seat, they should pull over on the right side of the road. They don't do it there all the time because it's not optimal for their route. So they're making a compromise because they're saying, I want the route to be optimal, and the driver needs to make a right. So if they drop it off on the left side here, then they're going to have to cut over millions of traffic to get make a right. It's probably not very possible for them to do that. So what's your cost benefit there? They're saving money because it's more optimal what they're doing, but they're also at the same time risking safety of someone's life. Yeah, I see that too, Senor. I don't know what's going on. Look at all look. It's like some sort of a little light show across the street. I don't know what we're doing.
You say
I noticed it.
Yeah, alright, we can all look at it. It's a green laser. I'm not sure what they're really doing, that's why it's coming through. You see that too? You saw that green laser coming through here. Can you guys just lower the blinds? Don't look at the director, guys. You really shouldn't look directly. Those are the blinds. You saw that too.
I did not see that.
It's not a laser, you shouldn't do that. You don't see people who do that in the airfield, right?
Yeah, you can get
Look at that, it's a lot of trouble.
Yeah, it's definitely.
Oh, you're doing something, I don't know.
It looks like it's the
saw it. It's over. It's just a green laser being shot across. It's not got the time down pat yet. No, like about 55? Alright, so in 5 minutes we'll pause the lecture, some worship class, and get into this. I would like the lecture for 60 minutes, not 50 minutes. So I'm going to just get across what I want you guys to know, generally about this. Okay, so the next slide is about the 4 main branches of engineering. And I say 4 main branches because these were the 4 historic main branches. Nowadays, there's many more branches, and there are subgroups of all of these. So, what do you notice is not here? That's the one that's most obvious that we use every day now. Computers. They fall into electrical. So, if you're going to major in computer engineering, you start off your freshman year as an ECE, Electrical Computer Engineer. All electrical and computer engineers work together in the first year. And then after the first year, you recognize, am I into software? If I am, I'm probably going to be a computer engineer. If I into hardware, I'll probably be an electrical engineer. Or maybe into both. And you have 1 degree with a minor or a concentration in the other. So when I was in college, I was mechanical, and we were able to do what was called a mechatronics concentration, where mechanical engineers studied electrical stuff. I didn't do that. I was in math and electrical. I was a math degree concentration in an engineering field. You okay?
Yeah, I'm looking for my schedule.
So in different fields, you'll have sub-branches that correlate to different topics. So if, I think, did you say aeronautical? Was it you at one point? Yeah. So it's clearly not one of the topics up here. But that would most likely fall into mechanical because it involves moving parts. Things that involve moving parts with structures are mainly mechanical. Things that are static, not moving, are mainly civil. Now, there's obviously overlap. Because things that are sometimes moving and sometimes stationary fall into both, right? So that's the general trend, though, or that civils work with static objects. Not always the case, like a bridge. To draw a bridge will open and close. That's civil engineering, obviously. Yeah. Chemical. So materials science or materials engineering. So when I was a freshman, I was between like the chemical portion, I loved chemistry, mechanical, because I just thought it was the most broad, and then computer, because I really enjoyed computers at that time. I'm recording, so everything you should be able to see. Computers, because I really enjoyed computer engineering at that time.
So on my schedule says this.
Yeah, but the next half of the year, we're going to see
Yeah, I won't go ahead.
Sure. And I'll just go over all the engineering again. Is there a reason you have to go here?
Well, it says on the schedule.
Don't worry, I just went to Mr. Joseph 10 minutes ago and so if you're in class, he goes, oh, it's not my class anymore, it's your class. So he doesn't even think you're in that class. So unless you really need to go there, I'd rather you stay here for the safety side. So what was it saying? Materials, right? Stuff materials. So materials science or materials engineering is really a subset of chemical engineering. It's one of those that falls in that category. So these are the main 4 that were historically the main 4 that were used. Let me give you some background about where they came about. So chemical engineering first started with several things. First, fuel. Fuel was a big component. Guys, stop. Fuel was a big component when it came to chemical engineering. Because at that point in time, when we really started looking into like machines, we had to think about things like steam engines, or other types of engines that run on gasoline or oil, or if we were using kerosene to warm up a house. So fuel was a big thing with chemical engineering. Another thing that was big with chemical engineering had to do with manufacturing. So manufacturing items, whether you are making clothing, whether you're dyeing certain clothes, it was chemical engineering back in the beginning. Whether you are making what are called casts and dyes. So like if you want to make an object, usually you make a cast out of it. It's called sand casting. And then you can fill it with like a molten metal. And then it solidifies. It was all chemical engineering that came about from it. Say again? Sand casting, yeah. It's a really interesting technique. I learned it in grad school in factory course. Civil engineering was mainly used, civic, for human life to help you on an everyday basis. Bridges, roads, buildings, tunnels through mountains, all civil engineering with that. Dams also going on here. Electrical engineering. Basics of electrical engineering came about when we started recognizing or discovering the use of electricity. Now, it has advanced a lot more than that since then, but the original idea was like optics, for light, for even corrective lenses. Electrical engineering was utilized for this. Let's see. The original computers and calculators. Nowadays, for controls, for optics, for fibers, for different instrumentation and devices. So if we want to test something in a lab, it takes the electrical reading to understand the readout from it. So there was a lab that I was in mechanical engineering where you put a specimen of metal, and then you apply a fix to each end and pull it apart. It's called the tension test. And it's metal. Eventually it starts to bow, like a bow tie in the middle, and then it pops, it snaps. There's no way you can measure that without electricity, without some sort of computer system in place with sensors. So nowadays, electrical engineering and computer engineering is probably the most important engineering that exists, because we are in a world now that involves everything with electricity and computers. Last was mechanical engineering. Mechanical engineering originally started with war, catapults, trebuchets, building walls that could withstand certain attacks. So really, it had to do with war, where mechanical engineering really began. And then from there, it picked up. After weapons and aircrafts and stuff, it became transportation. It became engines, building engines. One that's a big one had to do with vibration analysis. Mechanical engineering do a lot with vibration analysis. There's a story I'll tell you guys about BMW. So I forget what year it was. I was told the story in my second year of engineering, that's why I know it. So BMW had a certain model of their car. And let's see, my second year of engineering was in 2006. So before 2006, one of their car models was unfortunately having problems in certain speed ranges. So between like 50 and 70 miles an hour, or 60 and 70 mile an hour, so some range of speed, what would happen is, under certain weather conditions, the passenger door, would start to vibrate. And vibrate like ridiculously, to the point where like drivers were getting concerned about safety, that the door was going to tear off. And somehow, when BMW did all their testing and modeling, they didn't take into account this specific scenario, these specific conditions, these weather conditions at these speeds in this much air or flow, wind coming out of the car. But the perfect storm, if you will, like all those things combined, would cause this to happen. So mechanical engineers studied it by placing springs. Remember we talked about springs last year, how springs are used all over the place. So they attached springs to the door to model the vibration of the car, to see what parts of the door were vibrating at different rates, so they could then control those vibrations and minimize them. The same technology for that is now used in fans. Those bladeless fans, or the fans that have like almost no sounds in them that do have blades. If you have like an old school industrial fan, those things are loud as hell, like really loud. Well, you wouldn't want that in your house. So these new fans use technology that exists to minimize the vibrations that occur as a result of some sort of rotary motion. And it's usually cyclical rotary motion.
Is that why when you like shout into the old fans, it like distorts the
We go whoa like that. It has to do with the sound waves going through the passive blade, yeah. So and that's the vibration of your voice because it's cyclical. It's having a vibration that is causing it. Anyway, an example of mechanical engineering application of that. I'm going to pause at this point for the lecture portion. So you can stop here. We'll pick up the